Hi, I'm Chandu Disanaika and I'm currently doing my Bachelor's of Cybersecurity, and this is one of my assessments from the subject Computer Systems. So this is the assessment. It is about implementation of hack CPU. So now I'm going to discuss the hack CPU implementation. So I use a presentation to discuss about hack CPU. Okay then, this is the CPU architecture. Uh, when considering about that, this diagram represents the proposed design for the CPU architecture that I will use to explain and implement the CPU's HDL code. The CPU is made up of a number of logic gates, including the multiplexer, ALU, A register and D register. To begin with, let's start with an abstraction. This chip by hiding all the logic gates in the diagram so that we can quickly identify the input and output pins of the CPU. The first step to implement the code is to derive the API of the CPU, which specifies the chip name, input and output pins, and the function of the CPU. So in this slide you can see the input and output pins of the CPU. So now that we can clearly see the inputs and outputs of the CPU as shown in this diagram, there are three inputs coming into the CPU from different sources: the instruction memory and the data memory. The instruction input comes from the instruction memory, which is the value of the selected instruction memory. So the instruction can either be A instruction or C instruction. On the other hand, in M is the value of the currently selected data memory register and is the value that the CPU used to perform its operations. So next, the computer system. Here we can clearly see a diagram that further demonstrates how the CPU is interconnected with the data and instruction memories. Here we can clearly see that the CPU clearly receives the instructions input from the instruction memory and also accepts the value of the chosen data. That means selected data. So memory register as one of its inputs that the reset input indicates whether to return the CPU to its starting state or whether to restart the operation from start. In addition to the inputs, the CPU also includes a number of outputs that are connected to the instruction memory and data memory as well as these outputs are called as you can see here write M, out M, address M, and program counter. Going back to the given CPU architecture, we can see that the CALU provides an output that is written to the data memory. So in order to do this, the ALU must specify a few things. First, including the data that the CPU will write into data memory, which is stored in the outm, and the address of the write operation in the data memory. So lastly, the output that permits the CPU to send information to the data memory is the program counter, which contains the location of the following instruction. The following cycle, the CPU will fetch, decode and execute that instruction. Now that we have identified the input and outputs of the CPU architecture, now we can implement the code of the CPU and discuss how it works and how it operates. I have broken down the code into parts so that it will be easy to explain and understand how the code is working. This is the header section that specifies the CPU interface. It consists of the chip name and the names of the inputs and the outputs. As shown in this code, the input pins of the CPU consists of 16-bit in M. In the beginning of the code, the line specifies the interface of the hack CPU, which consists of the chip name, that is CPU, and the input and output pins as I mentioned before. The input and output pins correspond to the design of the hack CPU. First part of the code has 3 gates: NOT gate, an AND gate, and a multiplexer, that means mux 16. These allow the CPU to perform functions and specified operations. So there are two types of instructions as discussed before, namely A and C instructions. In the first line of the code, using NOT gate, we will get to know if the instruction coming from the memory is an A instruction or not. The CPU decodes the 16-bit instruction from the data memory into single-bit code and a 15-bit value. If the code is 0, it's an A instruction. If the code is 1, it's a C instruction. If the instruction is an A instruction determined by the NOT gate, the specified 15-bit value is stored in the A register. So, however, if the instruction is a C instruction, it goes to the ALU. ALU means arithmetic and logical unit. So, after performing the required computations, the ALU output is then sent to the A register. In the real code, an AND gate is used to check if the instruction is a C instruction. Additionally, a 16-bit multiplexer is employed to choose whether the ALU output should be stored in the A register or not. This slide. In this part of the code, there is an OR gate. Load bit in the A register would be 1 if either the A instruction of the LU output is fed to the A register. So next, A register takes the output A register in from the multiplexer and load A as its input. It has A out, which is used in generating the value inside the A register. Then mux 16 takes the output A from the A register and in M, which is the currently selected value in the data memory. So then it selects whether A or M would be fed or loaded in the ALU, which would depend upon the 12-bit instruction value. So further, AND gate is used, which decides whether the ALU output should be loaded inside the D register or not. Output will only be loaded if both the parameters or both the conditions will be true, that is the instruction is C instruction and the 4th bit of the instruction is. Then in this slide, this part of the code contains the ALU, which performs the computation part. It computes based on what two inputs, which can be the values from the D, A and M register, and it has 6 control bits that are ZX, NX, ZY, NY, F and NO, that indicate which function will get computed to get the desired output. It provides the output ALU out as the result of the computations. It also has 2 output pins, namely ZR and NG, which determine the property of the result. If the output is 0, then the ZR is set to 1, and if the output is less than 0, then NG is set to 1. Further, we have 2 O16 gates and 1 AND gate, which are used to determine whether the data is to be written inside the data memory or not. The first O gate, that means O16 gate, gives the address of the RAM location, and the second O16 gate provides the value that is to be written at that particular location. AND gate is used to write the output only if both the input condition are true. Then in here, the final slide, AND or NOT gates are used to determine the jump conditions of the program counter. The jump bits are the ALU output determines the PC's load bit. These codes determine the jump instructions, check the ALU output and determine whether the conditions are fulfilled or not. Therefore, the PC will be loaded with the value that will ask the CPU to jump to a specified instruction if the instruction is the C instruction and conditions are fulfilled. However, PC is increment by default if PC is not loaded. And finally, this is how the CPU and its HDL code works. So thank you, and I think all the stuff are clear, and my assessment part is 100% clear. And so finally, thank you.